All right. Hi, everybody. And we're going to start a new chapter today. It's actually a very quick chapter, and it's all devoted to this notion of computing a determinant. So now you remember always what we'd like to have at our disposal is a very quick and easy way to check if something happens in mathematics, where that something is typically difficult to show or determine if it exists using the definition. And case in point, finding the inverse, if you if you're given a matrix and you don't know if it's invertible, and the only way to find if it is to go through the process, that could be an absolute nightmare if it's a big matrix. And only to find it's not invertible by the end. So kind of a letdown. So what I want is a nice way of determining if I have a matrix, how do I determine if it has an inverse without having to find if it does? All right, and so that's where we introduce this notion of a determinant, right? And so the determinant, you can only do this for a square matrix, which is fine because we're only going to link it to invertibility anyway, and those can only occur for square matrices. So it's a number, and we're going to denote it as det of a for, guess what, determinant. And sometimes you'll see it with absolute value bars. And so there you just have to be careful of the context, right? I mean, we overuse notation mathematics incessantly. Um, so just make sure you realize that if A is a matrix, that means determinant. We've already introduced this idea when talking about 2 by 2 matrices, right? At the very beginning of our discussion of invertibility, we didn't have the notion of a determinant. We wanted to wait until later to introduce that, but we wanted to get to the idea of an inverse, right? And so we introduced a very easy formula for computing the inverse by doing something to the matrix A with the diagonals and dividing by this number. And so here, the definition of a determinant of a 2 by 2 matrix is you simply, written in this form, you multiply A times D, so you multiply down that way, and then you subtract up that way, right? It's all you have to do. And so you get that number. And so we see right off the bat that if this number is 0, you would be dividing by that 0 to form the inverse of A. And so apparently if A is such that this is equal to 0, it doesn't have an inverse, right? So it's kind of a nice way of looking at it. So the conjecture is that there exists A inverse if and only if the determinant of A is not 0. At least that's a true statement in R2. I'm sorry, for 2 by 2 matrices. We'll see if it holds water later on for all n by n matrices. But for now, let's just compute, right? So the determinant of this guy, multiply down that way. So it's 5 times 6 minus 3 times 7. And so that's 30 minus 21, which is 9. And so I should label that. That's the determinant of A. Also up here, this is just an aside. For a 1 by 1 matrix, this is just for consistency's sake, right? Technically, every scalar can be written as a 1 by 1 matrix. The determinant of such a matrix is the entry itself, right? So that's just for definedness sake. Right? It's not undefined. It's like defining 0 factorial to be 1, right? It's not a provable thing. It's just that's how we define it for it to make sense for all cases. Okay, this guy here, let's determine the determinant of B. Well, you multiply down this way, so it's 2 times 10, subtract up that way. Notice here, you get 0. So we know from this observation is that there is no B inverse, but here in the original one, there is an A inverse. And we have a formula back in section 3.3 that you can use to find that. And this guy, this is important because it comes up when you're computing double integrals in polar coordinates. So you have a double integral that's in Cartesian coordinates, x and y. It's a nightmare to compute, but it turns out that if you change the coordinate system to polar, the resulting integral is much easier. And so this is the Jacobian matrix. The determinant of that matrix occurs as the fudge factor inside that new integrand in polar. So if you've seen double integrals already, you know what I'm talking about. If not, well, you're getting kind of a little preview as to why this would be useful, even in calculus. All right, but the determinant of C, multiply down that way, and then subtract up that way. But notice we already have another negative. So I'll put it in as minus sine theta times minus r. Just to remind you that you are subtracting here, but we're going to quickly simplify this. This is r cosine squared of theta, so there's two of those, plus r sine squared of theta. And yeah, you could yank an r out. And what we know is that since this theta is the same, cosine squared plus sine squared of theta is 1, that leaves you with just r. Okay, and so that is that fudge factor that occurs in double integrals. All right. Along the same lines about finding if a matrix is invertible or not, what if I just gave you a matrix that has an unknown parameter, and I wanted to know for what values of that lambda does the matrix fail to be invertible? Well, you'd say, well, I don't want to have to go through the whole formula. Let's just compute the determinant. So the determinant of A, you multiply down this way. So you have lambda minus 1 times lambda minus 3 minus multiply up that way, minus 4. And let's simplify that. We can FOIL that out. So first, outer, inner, last. Right, you get that. And so if you add the 4 or negative 4 and 3, you get that guy. So the claim is there is no inverse if and only if that expression is equal to 0. And well, that doesn't factor on the left, but we do have what that good old quadratic formula that we can use to find those values. And so lambda is equal to negative b plus or minus square root of b squared minus 4 times a times c all over 2a. Okay, just using the quadratic formula. And that simplifies to 4 plus or minus root 20 over 2. And then I can kill a 2, right? This is 4 plus or minus 2 root 5 over 2. Then factor a 2 out of the top and get rid of those. All right, so for these values of lambda, if I were to plug them into that original matrix, the resulting matrix would have a 0 determinant and hence would not be invertible. Okay. All right. Good deal. So now the question is, well, I can define a determinant for a 2 by 2 matrix. How do I do it for a 3 by 3? Right, and so one way, the notion of a determinant is defined recursively. So the idea is I could always define a determinant of a 3 by 3 by whittling it down to a bunch of 2 by 2s. Right, and so the way we define a determinant for a 3 by 3 is the following. We want the determinant of that matrix. So I'm going to take this guy, let's say, cross out mentally the row in the column containing that guy, okay, and multiply a times the determinant of what remains. Okay, so this here is called a minor matrix, right? So the minor matrices are the ones that are smaller in dimension. Okay, so you're breaking this down into a bunch of small matrices times constants, and then you have that computation. And then I have a minus here. That minus comes up for a very particular reason called when we define the cofactor. But for now, you just know that if you're using the top row, there's a minus there. B times the determinant of what remains, right? If you take the row and column containing B and throw it out. And then you do the same thing, you add C, throw out mentally the row and the column containing C, and take the determinant of what remains. Right? So if you've ever seen the notion of a cross product, you've done this where the top row is the I, J, and the K. Right? And so we've seen that before in that case. If not, well, this is how you do it. All right, so let's go through, let's compute. So we have, for this 3 by 3, you have 2 times the determinant of what remains if you mentally throw out the row and column containing 2. So that would be the matrix 4, 4, 0, minus 5. Then we put the minus in. That minus is part of that formula. The B, which is this guy, times the determinant of what remains. If I throw out the row and column containing that, that gives you the matrix with those 2 columns. So it's 1, 1, 4, and negative 5. And then plus the 3, times the determinant of what remains if I throw out the row and column containing 3, which is just these two guys, 1, 1, 4, and I think that is a 0. All right, it's easy as that. So we whittled it down to a bunch of cofactors. Now we just compute them. 2 times this determinant is minus 20, plus 1 times this determinant, minus 5 minus 4 is minus 9, then plus 3 times this determinant, 0 minus 4. Right, and so you get minus 20, or no, minus 40, minus 9 is minus 49, minus 12 is minus 61. All right. So if our theorem stands up for 3 by 3, that determinant's not 0, so this matrix would have an inverse. Okay. And then here, I will let you do this one on your own. This is what arises if you're taking a cross product of this vector and that vector, right? So this is more of a application in Calc 3. What you will get in the end, I'll say just do the same process, but what you get in the end is minus 7i plus j plus 10k. Okay, so you can actually try to show that and see if you get that. All right. So now let's actually go through and give a little bit of the terminology. When I broke that 3 by 3 down into 3 pieces, the determinants were called the minors. Right, so I was starting to say that terminology without actually defining it. So the smaller determinants you have to compute are called minors. They're smaller, they're minors of the original matrix. All right, and then for a general n by n matrix, you're going to define a number, or you're defining a new matrix, right? So remember how we said we're throwing out the row and the column containing the number that we used in that top row. Well, it turns out you can do this no matter what row or column you want to use. And so once you've chosen the row or the column you're going to use to break the original matrix or originally determinant down to cofactors, or into minors rather, what you do is you multiply -1 to the power is the row plus the column that number happens to be in. And so if you look back at our example here, let's go back to this example. So notice here that the 2 was in the first row, first column. So I'm going to multiply -1 to the 1 plus 1 times the 2, but -1 to the 1 plus 1 is just 1. This guy, you don't have to memorize that negative now. Just say plus. Here is the number. The -1 happens to be the entry, but the power of -1 that I multiply it by is -1 to the row plus the column. But notice the row plus the column is 3, and so -1 to the third is -1. That's where this negative is coming from in this particular case. And then plus 3 times -1 to the row and the column, that's 1 plus 3. -1 to the 4 is +1. And so that's why this guy happens to be positive. All right. And so in general, I can do that. It doesn't matter if I choose the top row. I can choose any row or column that is convenient. And by convenient, I mean you want to identify the number of, you want to use in general the row or column containing the most zeros, because it'll blot out more of the determinants you have to compute thereafter, right? So that's definitely beneficial. All right. All right. And so what you do is what we just did for that 3 by 3. You choose a row and column, and then you just go through and form these matrices by killing off the row and column containing it, multiplying that determinant by the appropriate power of -1 times the entry in that row and column that you killed in the first place. All right, so let's go through and show this for just this particular matrix. Let's actually use a different rows and columns and show kind of you get the same result no matter what. But sometimes it's easier than others. All right, so the standby is using the first row, right? Because that's what when you introduce the cross product, that's the first thing you do is that. All right, so let's do that. The matrix or the determinant of A happens to be 2. Or it's okay. It's -1 squared times 2, because I'm in the first row, first column. That's where that 2 is coming from here. Multiply by the number, and then the determinant you're getting is the row and column that contain 2 are thrown out. So the determinant of what remains is that guy. All right. And then I'm going to add to that -1 to the, I'm here, first row, third column. Sorry, first row, second column, rather, times the determinant of what remains if I kill those. All right. And notice here, that's -1 to the third. That's just -1. And that's just 1. And then plus -1 to the row plus column is 4, times the determinant of what remains if I throw out the row and column containing it is that. If I were to simplify this, I have 2 times 14 minus a -6. That's 2 times 20. Then I have 0 minus 0 is 0. 0 minus 0 is 0. I just get 40. Right? Notice these zeros in a column kill off the determinant because you're always multiplying one of the guys in the other column by that corresponding entry in the other. All right. If I were to use the second row instead, so I didn't like to use the first row. Let's use the second row. Well, here then, if I choose to do that, I need to multiply by -1 to the row plus the column. I'm in the second row plus the first column. 0, that's the number, times the row and the column containing 0 go away. And so I'm going to throw out this and that. So I have to take the determinant of what remains after throwing those out. That's this guy. Okay. And then plus, I go over to this guy. Okay. I think that's a 7, right? Yeah. So I have -1, second row, second column, that's 4, times 7, times the row and the column containing 7 go out. I have a 2 and a 4 and a 0 and a 2 left over. Right after I threw those guys out, those are what remained. And then plus -1 to the 5th. So I'm using this guy. That's the second row, third column. 2 plus 3 is 5. And then cross out the row and column containing it. And then what I get left over is 2 - 3, 0, 6. Okay. Let's simplify those. All right, so I have this plus that. All right, so I have -1 to the third times 0. So this wipes out. I don't even have to worry about computing that determinant. I'm multiplying it by 0. Over here, that's +1 times 7. 2 times 2 is 4, minus 0, that's just 4. And then here, that's a -1 times 12. Did I miss a sign? I don't think so. Wait, did I miss? Hold on 1 second. This sure turned out to be the same thing. So did I have... Oh, no. Row in column. So the row is 2 plus the 3. Where did that foul up? So I have row plus column. Oh, that's why. There's a -1 here. Sorry about that. So that was right. I just forgot to multiply by the -1 that was there. Oh, otherwise I thought, my God, we're not getting the same thing. But we are. Sorry. So the -1 here, remember how I multiplied by the 7 here and the 0 that was there? I have to do the same thing here. I forgot that -1. So that is -1 to the 6th. That's +1. The determinant was 12. And so you get 28 plus 12 is 40. Okay. Good. So I get the same thing back. This one's a little less annoying in the sense that we have a 0, so it killed one of the determinants. By that same sort of reasoning, why don't we use, now we can't see the original matrix. The original matrix, since I wrote all over it, is this. All right, this is our original matrix A here. And so here, it would be a lot easier just to use the first column, right? Because if I'm multiplying determinants by the entries in a column that I'm using, I'm going to kill off these columns. I'm going to get zeros. And so what I'll do here is I'll choose the first column instead. These will be the ones that generate the negative ones and the entries in front of the determinants. So I have negative 1 squared, first row, first column, times 2 times the row and the column containing, if you throw out the row and column containing 2, you get that determinant. Plus, well, the next two are 0, so it doesn't matter. I just get a plus a 0 at the end there, right? So I don't have to bother with those. Good. And so the determinant is just this guy. Negative 1 squared is 1. That's times 2. 14 minus a negative 6 is 20. And I indeed get my 40 back, right? So that's much easier to deal with. All right. And so that's how you compute. You can switch no matter which row or column you're using. You can switch them up using that. Okie doke. Now, let's actually just do, I'm going to choose one of these to do. We don't need to do 17 million examples. But let's actually do part B. So I'm doing the same thing. We want to compute the determinant, but now of a 5 by 5, mercy, right? But why don't we just notice this is an upper triangular matrix, right? And so upper triangular matrices are really kind of easy to compute the determinant of, as we'll see, right? So the determinant of this matrix, let's call it A. The determinant of this matrix A, we're going to use the first column. And so I get 3 times negative 1 squared, 3 times the determinant of what remains if I get rid of that row and column. And so I have a 4 by 4 that I whittled it down to. And 0, 0, 0, 2. Okay. And then I don't have to worry about writing the other 4 because they're multiplied by zeros. Oops. Sorry about that. So let's do this. Okay, so I have 4 zeros here. I don't need to worry about those. Just get 0. But now let's whittle this down again. I'm not done. I don't have a number in my hand yet. And so this is just 1 times 3. I want this determinant. Well, let's actually use the first column again. It worked pretty well the first time. These zeros kill everything except for that first one. So here I have 3 times, I'm in the first row, first column again, times the entry, times the determinant of the matrix obtained by killing off the row and column containing minus 2. That's 5 pi 12, 0, negative 1 root 7, 0, 0, 2. Okay. Well, good. We're still not done. All we can do here is simplify that. That goes away. Well, we have a 3 by 3. Let's do it again. Choose the first row. So we have 3 times the 2, negative 1 to the 2 plus 2. I'm always using that upper left entry, so it's always going to be negative 1 squared, which is the 1, but times the determinant of what remains after you throw out that row and column. That's that. Now we have a 2 by 2. Oops, and I forgot the 5 again. There's the 5. All right. So now we have a 2 by 2. We don't have to break it down further. Just compute. I have 3 times 2 times 5 out in front. Right? Negative 1 times 2 minus 0. That goes away. That is a number. That number turns out to be 6 times 5 is 30 times 2 is negative 60. Right? I believe at least. Okay. So now, what do we do? Notice this. If we have at the very beginning, if we look at this matrix, right? If we look at, oh, that was a negative 2. I'm always following these negatives up. Here's a negative there, a negative there. It turns out to be positive 60. Sorry about that. I just made a slight typo on this term if you're following along here. That was a -2, so that should have been negative. I forgot that I dropped the negative on that. All right. But the point I want to make here is that if you look at the original matrix, that was upper triangular. If we just multiply the entries on the diagonal, 3 times -2 times 5 times -1 times 2, we ended up getting the matrix determinant in that case. So if a matrix is upper or lower triangular, as it turns out, meaning that above or below the diagonal you have all zeros, then its determinant is very easily obtained if you choose the column or the row that contains all but 1 0 every time, because that'll always blot out everything but just one of those determinants. And these numbers out in front are always the upper left corner of that matrix, which turn out to be the entries on the diagonal. So that's a nice sort of handy thing to do to yield if you have such a matrix. If you don't have a matrix that is upper triangular, what we would like to do is convert the matrix to echelon form, to echelon form, because that will be an upper triangular matrix in the end. We have to see, however, what that does, what doing these row operations does to the determinant. So we have to be a little bit careful with piddling around with a matrix, but we'll see that in the next video. All right, so at the moment, just go ahead and get used to computing determinants using cofactor expansions and whatnot, and see how that goes. All right, take it easy. I will see you later. Bye.